A true solid's molecules are ordered in a repeating crystal lattice structure, whereas a glass's molecules are disordered and effectively stuck in place. To be created, the material needs to undergo a glass transition. The glass transition is a phenomenon that occurs as a liquid is cooled or compressed at a sufficiently rapid rate so that the molecules don't have time to reorganize. Once through the glass transition, the material will begin to behave like a solid object. But if the material were left alone for long enough, it would continue to evolve towards its crystalline state. Materials which exhibit solid-like behaviors at short times and liquid-like behaviors at long times are known as viscoelastic. The particular type of viscoelastic material we study are polymers. Polymers are everywhere in our daily lives. In our phones, our cars, our houses, even in our clothes. Because of the extreme prevalence of these materials, it is vital to understand their physical properties. This is our de-wetting lab, and here we focus on studying ultra-thin polymer films. We use a self-built piece of equipment to measure the glass transition temperature and mechanical properties of these films, which are sometimes only a few nanometers thick. A normal rheometer can't measure anything close to this size, so some clever French scientists by the names Boudigal and Frétigny came up with a different way to do it. The basic concept of liquid de-wetting is this. A heated glycerol bath supports a thin polymer film, and the relative surface tensions between the materials induce stress in the film, causing it to shrink, or de-wet from the glycerol. The film's thickness can then be calculated using the change in surface area over time. From these values, standard mechanical properties such as modulus and compliance can be extracted. One of the odd things about these small-scale films is that below a thickness of about 40 nanometers, the glass transition temperature begins to rapidly drop. This means that once your material gets this thin, tiny fluctuations in temperature can drastically alter its mechanical properties. Take one of the thinnest films we've studied, around 10 nanometers thick, and scale it up until it's as tall as me. If you then drop it in my backyard, it would be much bigger than the house, much bigger than the neighborhood or even campus, even bigger than the city of Lubbock. In fact, after scaling it up, the 6-foot thick film would cover more area than the entire state of Texas. To make a film, we first need to create a very dilute solution of our polymer in a suitable solvent. Today we will be using linear polystyrene and toluene. To make our thinnest films, we only need about a 0.1% solution by weight. These can be very difficult to work with, so for the purposes of this video, we will make a 3% solution. This should result in a film around 120 nanometers thick. Once the solution is made, we let it sit in the rotating mixer overnight to make sure it's as thoroughly mixed as possible. To create such thin polymer films, we use a process known as spin coating. We center a cleaved square of mica on the vacuum, fresh side up, then drop by drop add enough of our solution to provide full coverage. The lid is closed and our sample is spun at 2000 RPM for 30 seconds to remove excess solution. Once stopped, we have successfully made an ultra-thin film. But there may be small amounts of toluene left over, so next we'll head over to the oven. The oven is set to 20 degrees Celsius above the material's bulk Tg. This temperature choice serves a couple purposes. In addition to evaporating the remaining toluene, it erases the residual stresses caused by the spin coating process, allowing the de-wetting measurements to represent a totally fresh material. After 30 minutes, the oven is switched off and left to cool. Once back at room temperature, the sample is almost ready for the experiment. Down in the de-wetting lab, we will first turn on the heaters since it can take a while to heat up the glycerol. In the meantime, we can cut our sample into 9 smaller squares. One of these will be transferred onto a silicon wafer and set aside so its thickness can be measured with the AFM. This means that we can run up to 8 experiments with a single sample. To transfer a film onto the de-wetting device, we use a razor blade to shave off the edges of one of the small squares. The remaining film should be roughly a 5 mm square. The film is then lifted off the mica using a water bath. The key here is to go slow and at a shallow angle. Do not try to force the film to come off. This will help it stay in one piece. Next, the film is transferred to 2 separate glycerol baths in succession to remove as much water as possible. Once the glycerol in our device is done heating up and the temperature is stable, we set the camera to take 1 picture every second. Now we can load our film onto the device. The type of experiment we want to run will determine how long we will record. De-wetting at temperatures far above the glass transition could only last 15 minutes, or maybe even less. On the other hand, one experiment that was done very close to TG took 10 whole days to finish. While waiting for the experiment to finish, we can measure the initial thickness of the film. We make a few razor cuts in the piece that was set aside earlier in order to provide a baseline for the thickness measurement. The AFM works by vibrating a cantilever with an extremely sharp tip and scanning back and forth across the sample. The features of the sample cause deviations in the cantilever vibrations, which are recorded as changes in height. Once the scan is complete, we essentially have a topographical map of the sample. The thickness can then be measured using the change in height between the film and the wafer. Liquid de-wetting is just one of the research interests of the McKenna Group. Some others include nanobubble inflation, colloidal dispersion rheology, and the relaxation of circular DNA.